Hi, everyone. I'm Sean Vitousek. I work at the U.S. Geological Survey in Santa Cruz, California. And this is a talk about the topic of long-term shoreline change modeling. The outline for this talk is as follows. I'll give a little bit of intro on the problem of coastal change, talk about various approaches to long-term coastal change modeling. And by long-term, I generally mean on the scale of days to decades. I'll talk a little bit about some shoreline projections that we've made with calibrated models with the data coming from satellites. I'll also talk about some of our recent applications in the US, and also I'll talk about the ShoreShop community testbed modeling effort and some conclusions. So when you're talking about long-term shoreline change, generally the question that you're asking is, where is the shoreline going to be at some point in the future? And there are many subtopics to this, including how are beaches affected by sea level rise? For instance, as sea level rise goes up, where is the shoreline going to be in response to that? How far inland is it going to retreat? Likewise, how are cliffs and dunes going to erode in response to sea level rise? As you get increased wave attack to these features, they're inevitably going to erode faster than they have in the past. So trying to quantify that. Also, how does current and future fluvial sediment supply affect beach widths? Here you can see an example of a river in the Santa Barbara area and how much sediment is being delivered to the coast associated with a big rainfall event. And finally, how do beaches and dunes respond to storms? How quickly do they recover? Are things like nature-based solutions like artificial beach nourishments and dunes sustainable? The practice of adding sand to the beach, how long is that going to last? So the reason those questions are fairly complicated to answer is because processes like flooding, hydrodynamics, oceanography, and sediment transport processes are multi-scale. Coastal hazards like flooding and coastal change exhibit a very wide range of processes, interactions, and variability across space and time. So it's difficult to understand how the accumulation of those processes will cause geomorphic change in the future. One really nice advantage on the modeling hydrodynamic side is you have a universal governing equation, which is the Navier-Stokes equations, which represent conservation of mass and momentum of a fluid. And this equation is valid for any and all scales. So solving this, you'll get a pretty good projection of how the physics will change. On the other hand, there is not a universal equation governing sediment transport. The only thing that would be sort of universal is a conservation law, having sediment be conserved. However, there's a lot of sources and sinks and other uncertainties associated with how much sediment is being picked up off the bed and how is it being deposited on the bed in a turbulent flow field that make it much more difficult to model. And so inevitably, what you need to do with coastal sediment models is you have a model that's tailored to specific processes and scales. And at the low end, you can have physics-based models that are coupled hydrodynamic and sediment transport models that resolve small flow features and sediment transport in those flow features. And for modeling coastal change at the large scale, it's much harder to do with those models. And instead, you often have to resort to some sort of data-driven model for how things are going to change in the large scale. In the middle, there's been a new class of models, sometimes called hybrid models, that sort of leverage some of the advantages of each approach. And there have been a number of models that have been developed. Here you see a recent review by Hoagland et al. Showing some different domains in terms of shoreline, barrier, marsh, lagoon, and some of the models that have been developed to deal with coastal change on long time scales associated with different scales and processes. So looking at some of the end members of the coastal change modeling approaches, on one side you have physics-based models that compute coupled hydrodynamic wave sediment transport models, like Delft 3D, Mike 21, X Beach Coast. And on the other side, you have classic data-driven models or historical shoreline analysis models, with the classic model being a historical shoreline erosion rate analysis where you have data or shorelines coming from historical aerial photos or LiDAR that represent the shoreline position at different times in the past. And by fitting a trend to those, you can see how the shoreline is changing over time. There's advantages and disadvantages of each modeling approach, and some of the main ones that I'll cover here include, the physics-based models treat the most important physical processes involved, which is a huge advantage. On the downside, they're difficult to apply for large space and time scales because they're computationally expensive. They're also difficult to integrate with data. And also the performance for subaerial beaches is relatively limited, except they do perform very well for large storm-driven erosion events, but not as well during recovery. On the other side, data-driven models are simple, fast, and easy. They're constructed from real shoreline data, and so they're amenable to large-scale simulations. One of the downsides is the prediction is often only as good as the quality and quantity of data applied, and shoreline data is notoriously sparse. So there have been models developed, hybrid models like Cosmos Coast that I'll talk a little bit about, that can leverage some of the advantages of physics-based and data-driven models. And this is kind of an area where the field is trending. So this is an example of the model Cosmos Coast, the governing equation that it solves at the top here, which represents the combination of cross-shore transport, along-shore transport, shoreline trends, and effects due to sea level rise. In essence, it's basically a 1D conservation of volume approach in the longshore direction. And you can see different processes involved in terms of longshore sediment transport, cross-shore sediment transport in response to waves, cross-shore transport in response to sea level rise. And if you want to look at some of the model code or anything like that, you can use the QR code. So here's an example of Cosmos Coast applied in Southern California in La Jolla Shores in San Diego. And essentially what you see is a model transect that intersects a bunch of historical shoreline data, which represent the blue dots in this panel. And the model predicts the shoreline position in response to time series of wave height. And whenever you have a mismatch between the model and the observation, it tries to calibrate the model parameters to better fit the data. So this is what the prediction looks like when you have 20 data points or something like that for shorelines. So the problem with this was that we really needed more data to calibrate and validate these models, especially in areas where they're unpopulated or they didn't have a lot of data. For instance, Scripps is a very famous beach where they've collected a lot of data because of its proximity to Scripps Institution of Oceanography. But there are many other beaches that don't have the same level of data coverage. And the solution for that was satellite data. Here you see an example of the tremendous amount of satellite data in these blue dots that you get compared to traditional LiDAR GPS survey data set. It really allows you to capture much more of the shoreline variability. And we have access to this sort of data for the scale of the entire coast of California, which is really nice. So whereas previous efforts used about 322 LiDAR and GPS surveys, some of which only covered specific beaches, with satellites that enabled us about a factor of 1,000 increase in the shoreline data, which is pretty tremendous. So talking a little bit more about some of the developments in coastal monitoring from space, I'll just show a few, including COSAT, which is a project out of UNSW Sydney, led by Killian Voss, that uses Landsat and Sentinel imagery to detect where the shoreline is over time. Another important development was some work by Arjen Leijendijk, a project called the Shoreline Monitor. Other things are Digital Earth Australia, which has developed a really nice data set of composite coastlines, and some new efforts out of the USGS called COSEG, which you can check out. So what those data have enabled is long-term, large-scale shoreline change monitoring and modeling across large stretches of coastline. Here's an example of the updated Cosmos Coast projections that we've made with satellite data for an example of Ocean Beach, California, where you see that the northern part is accreting and the southern part is eroding. And the data and the model sort of captures that behavior. A really nice thing about the satellite data is it's allowed us to calibrate and validate the models over the large scale. Validate meaning we make a calibration where we train the model on a certain period of time, say 1990 to 2015, and then validate the model by running the model for 2015 to 2020 and seeing how well the model does with data that it's not used to train on. And by doing that, we can see areas of good performance and areas where the performance is not so good. But we can do that on a very large scale. Here's another example of a modeling effort on the scale of the South Atlantic coast, where again you see the satellite data in blue, the model projection in red, and some uncertainty associated with the model projection in yellow. And again, this level of data has allowed us to validate how well the models are doing on a very large scale. And in this example, we see that the models are doing fairly well for straight beaches, but it's not doing as well. It's these purple dots for small barrier islands and at the ends of spits and capes where the coastal processes are very complicated. Another example is community model validation efforts like ShoreShop. The purpose of this ShoreShop, which was organized by Giovanni Coco at University of Auckland, was to try to answer the question, can we blindly predict coastal change? That is, we were given 15 years of shoreline data and corresponding wave data. We were trying to predict the next 3 years of shoreline change without being given the shoreline data. We were given the forcing condition with the waves, but we weren't given the actual shoreline data. So we tried to make a prediction of where the shoreline was. We recently completed an updated ShoreShop benchmarking project. This is ShoreShop 2.0, organized by Kristen Splinter, Yongjing Mao at UNSW Sydney. We got about 30 submissions to this project, and we're able to see how various models performed in the context of blind data, which is a very interesting benchmarking exercise. Here is some of the results of some of the best performing models for ShoreShop 2 compared to the data in black and the ensemble in gray. And what was interesting to see among the top performers were many of them were machine learning models. So for me personally, it was asking the question, are AI models eventually going to take our shoreline modeling jobs? And to that, I think the answer is probably yes. But that's okay. The future of shoreline change research, I think, is going to look very bright. And to me, what the future looks like is the combination of satellite data plus traditional models and advanced AI models for prediction towards the task of operationally monitoring and modeling where the shoreline is and where it's going to be in the future. And we talked a little bit about this in this recent review paper in Cambridge Prism's Coastal Futures, if you'd like to check that out. So just to conclude, the question of to resolve or not to resolve hydrodynamic processes is really an important question for long-term shoreline modelers. And I think for the purposes of long-term shoreline modeling, the answer to that question is you're probably not going to want to fully resolve hydrodynamic processes because they're just too expensive. Instead, you'll want to account for hydrodynamic processes like time series of wave conditions as a model input, but not necessarily have a model that specifically resolves waves, currents, turbulence, sediment transport, because I think that renders the simulation almost too intractable. But we'll see. Another conclusion is that satellites have transformed coastal science from a data-poor field into a data-rich field. We just now have such a tremendous resource of 4 decades of shoreline data from Landsat for anywhere we want in the world, which is just a tremendous asset to the field. And we can use that data to better calibrate and validate our models. Despite having all that data, long-term coastal change modeling is still hard, but satellite observations in conjunction with better models, both hybrid models and AI models, are enabling better predictions. And finally, I think that AI are going to take our shoreline modeling jobs eventually. The power of the new emerging AI algorithms in conjunction with virtually unlimited sources of data are going to make for some pretty powerful predictions. But until they take our jobs, I think we should try to seek a better understanding and better interpretability of our models, which will also lead to improved projections. And with that, I'll just say thanks very much for checking out my presentation, and I hope you found something useful and intriguing about long-term shoreline modeling. Thanks.